So here's a more mathematically rich example. Suppose that we have the language of rings and some structure for it, which satisfies our typical axioms for rings, and then consider the set of polynomials over those rings. Now, when I talk about a definable set here, it's got to be a subset of the domain, so I really will be talking about a definable set as a subset of the ring structure, not the polynomials, but there still will be an interplay here. So the set that I am going to define is the set for a fixed polynomial, the set of all elements in the ring which map to 0 according to the polynomial. So, for one thing, actually, I think the author has a little bit of a typo here. I think this really should be n, but basically just give names to your coefficients of the polynomial, and we will define a formula phi with a single free variable v, and in the set of free variables for v, and then a bunch of other free variables w, and many of them, just as big as the degree of the polynomial, and they will stand in place for the coefficients in the polynomial. And since we're not allowed to write exponent, but we are allowed to write multiplication as many times as we want, then we give a coefficient and multiply the free variable v by itself n times and proceed in exactly how you would expect to proceed until we get down to a coefficient with a single power of v plus a coefficient with no power of v, all set equal to the constant in the language 0. And this is a formula. You can check for yourself that whatever, if we collect together the coefficients of the polynomial into the, list A, then phi on VA, because that'll fill in the coefficients of the polynomial, this function defines the set. So, or the formula defines the set. So, in the next video, we'll have a proposition about decidability and undecidability, and it will assume background knowledge of the halting problem. So that in the next video.